Hello everyone, welcome to the course on cryptography. In today's class, we'll discuss few things about public key cryptography systems. So in this table, we can see some of the conventional and public key encryption. So what is required in case of conventional encryption and public key encryption? In case of conventional encryption, needed to work is the same algorithm with the same key is used for encryption and decryption. The sender and the receiver must share the algorithm and the key. Whereas in case of public key encryption, one algorithm is used for encryption and a related algorithm for decryption with a pair of keys, one for encryption and one for decryption. The sender and the receiver must each have one of the matched pair of keys, but not the same one. In case of conventional encryption, the very much needed for security is the key must be kept secret. It must be impossible or at least impractical to decipher a message if the key is kept secret. Knowledge of the algorithm plus samples of ciphertext must be insufficient to determine the key. Whereas in case of public key encryption, one of the two keys must be kept secret. It must be possible or at least impractical to decipher a message if one of the keys is kept secret. Knowledge of the algorithm plus one of the keys plus samples of ciphertext must be insufficient to determine the other key. So here it summarizes some of the important aspects of the symmetric and public key encryption. So to discriminate between the two, we can refer to the key that is used in symmetric encryption as a secret key. The two keys used for symmetric encryption are referred to as the public key and the private key. The private key is kept secret, but it is referred to as a private key rather than a secret key to avoid confusion with symmetric encryption. Now, taking a closer look at the essential elements of a public key encryption scheme, there is some source A that produces a message. So here we have a block diagram here, and we can see here some source A that produces a message in plain text in terms of x, which is consisting of x1 x2 till xm. There are m elements of x. These are letters in some finite alphabet. The message is intended for destination B. B generates a related pair of keys, a public key which is denoted as PUB and a private key which is denoted as PRB. PRB is known only to B, whereas PUB is publicly available and therefore accessible by A. With the message X and the encryption key PUB as input, A forms the ciphertext. Y is equal to Y1, Y2 till Yn. Y is equal to encryption of PUB, X. The intended receiver in possession of the matching private key is able to invert the transformation. X is equal to D of decryption of PRB, Y. So here we can see a public key crypto system secrecy. It's an adversary observing Y and having access to PUB, but not having access to PRB or X must attempt to recover X and or PRB. It is assumed that the adversary does have knowledge of the encryption A and decryption D algorithms. If the adversary is interested only in this particular message, then the focus of effort is to recover X by generating a plain text estimating X cap. Often, however, this adversary is interested in being able to read future messages as well, in which case an attempt is made to recover PRB by generating an estimate of PRB cap. So as mentioned earlier, that either of the two related keys can be used for encryption, with the other being used for decryption. This enables a rather different cryptographic scheme to be implemented, whereas the one block diagram as shown in this figure, it provides confidentiality. So the figures that was shown earlier and the figure in the next block diagram shows the use of public key encryption to provide authentication. So y can be written as encryption of PRA, x. X is equal to decryption of PUA, y. In this case, A prepares a message to B and encrypts it using A's private key. Before transmitting it, B can decrypt the message using A's public key because the message was encrypted using A's private key. Only A could have prepared the message. Therefore, the entire encrypted message serves as a digital signature. In addition, it is impossible to alter the message without access to A's private key. So, the message is authenticated both in terms of source and in terms of data integrity. In the next screen, the entire message is encrypted, which, although validating both author and contents, requires a great deal of storage. So here we can see a block diagram for public key crypto system authentication, which is consisting of message source as X from source A, which is given to encryption algorithm, and a key pair source, that is PRA, is given. And the public key is denoted as PUA. So the encryption algorithm takes place y is equal to encryption of PRA, x, that is given to decryption algorithm along with the public key. So after decryption algorithm, we'll get the output as X, decryption of PUA, y, and then we'll get the result, final result. So here it is prone to cryptanalyst, that is PRA. If a cryptanalyst knows the private key, then he'll be able to deduce this message or plain text. So each document must be kept in plain text to be used for practical purposes. A copy also must be stored in ciphertext so that the origin and contents can be verified in case of a dispute. A more efficient way of achieving the same results is to encrypt a small block of bits that is a function of the document. Such a block, called an authenticator, must have the property that is infeasible to change the document without changing the authenticator. If the authenticator is encrypted with the sender's private key, it serves as a signature that verifies origin, content, and sequencing. It is important to emphasize that the encryption process, as shown in the diagram, it does not provide confidentiality, that is, the message being sent is safe from alteration but not from eavesdropping. So this is obvious in the case of a signature based on a portion of the message, because the rest of the message is transmitted in the clear. Even in case of complete encryption, as it is shown in this block diagram, there is no protection of confidentiality because any observer can decrypt the message by using the sender's public key. So it is, however, possible to provide both the authentication function and confidentiality by a double use of this public key scheme, and that is shown in the next block diagram here. That is Z is equal to encryption of PUB, encryption of PRA, X. X is obtained by decryption of public key with respect to A and decryption of private key with respect to B, Z. So we begin as before by encrypting a message using the sender's private key. This provides the digital signature. Next we will encrypt again using the receiver's public key. The final ciphertext can be decrypted only by the intended receiver, who alone has the matching private key, thus confidentiality is provided. The disadvantage of this approach is that the public key algorithm, which is complex, must be exercised 4 times rather than 2 in each communication. Thank you. Hello everyone, welcome to the course on cryptography, and in module 4 we are discussing about elliptic curve cryptography. So in this elliptic curve cryptography, the addition operation is ACC is the counterpart of modular multiplication in RSA, and multiple addition is the counterpart of modular exponentiation. This is to form a cryptographic system using elliptic curves. Like, we need to find a hard problem corresponding to factoring the product of two primes or taking the discrete logarithm. Consider the equation q is equal to kp, where qp belongs to ep of a comma b and k less than p. It is relatively easy to calculate q given q, k and p, but it is hard to determine k given q and p. This is called the discrete logarithm problem for elliptic curves. We give an example taken from the Saticom website, considering the group, and this is the group defined by the equation y square mod 23 is equal to x cube plus 9x plus 17 mod 23. What is the discrete logarithm k of q is equal to 4 comma 5 to the base p, that is 16 comma 5. So the brute force method is to compute multiples of p until q is found. Thus p can be written as 16 comma 5, 2p is 20 30, 3p is 14 14, 4p is 19 20, 5p is 13 10, 6p is 7 3, 7p is 8 7, 8p is 12 17, 9p is 4 5. Because 9p is equal to 4 5, q the discrete logarithm q is 4 5. So to the base p means it is 16 5 is k is equal to 9. In a real application, k would be so large as to make the brute force approach infeasible. In the remainder of this section, like, we can see the two approaches of ECC that gives the flavor of this technique. Analog of Diffie-Hellman key exchange. Key exchange using elliptic curves can be done in the following manner. Like, first pick a large integer q, which is either a prime number p or an integer of the form 2 power m, and elliptic curve parameters a and b. So for the previous equations, so this defines the elliptic curve, elliptic group of points like EQ of a comma b. Next, pick a base point g is equal to xi, x1 and y1 in EP of a comma b, whose order is a very large value n. The order n of a point g on an elliptic curve is the smallest positive integer n, such that ng is equal to 0, and g are parameters of the crypto system known to all participants. A key exchange between users A and B can be accomplished as follows. Like, A selects an integer na less than n, and this is A's private key. A then generates a public key which is equal to na into g. The public key is a point in EQ of a comma b. B similarly selects a private key nb and computes a public key pb. A generates the secret key k, which is a product of na into pb. B generates the secret k, which is a product of nb into pa. So the two calculations in step 3 produce the same result, because na into pb is equal to na into nb into g is equal to nb into na into g is equal to nb into pa. In order to break this scheme, an attacker would need to be able to compute k given g and kg, which is assumed to be hard. So as an example, we can take p is equal to 1 1, ep of 0 comma minus 4, which is equivalent to the curve y square is equal to x cube minus 4, and g is equal to 2 comma 2. One can calculate that 240g is equal to O. A's private key is na is equal to 121. So A's public key is PA 121 of 2 comma 2. as 115,48. B's private key is NB is equal to 203. So B's public key is 203, that is 2 comma 3. 130 203. The shared secret key is 121. So the secret key is a pair of numbers. If this key is to be used as a session key for some encryption, then a single number must be generated. Coming to this elliptic curve encryption and decryption, there are actually several approaches to encryption and decryption using this elliptic curves have been analyzed in the literature. But in this section, it's the simplest. The first task in this system is to encode the plain text message M to be sent as an XY point PM. Here we have a global public elements, that is EQ of A comma B, elliptic curve with parameters A, B and Q, where Q is a prime or an integer of the form 2 power M. G, point on elliptic curve whose order is large value n. User A key generation, selecting the private key NA should be less than n. Calculate public PA. Public key PA is a product of NA into G. User B key generation is similar to user A key generation, selecting the private key NB. NB should be less than n, and calculate the public key PB. PB is equal to NB into G. Calculation of secret key by user A, K is equal to NA into PB. Calculation of secret key by user B, K is equal to NB into PA. So this is the ECC Diffie-Hellman key exchange. This is the point PM that will be encrypted as a ciphertext and subsequently decrypted. But we cannot simply encode the message as the X or Y coordinate of a point, because not all such coordinates are in EQ of A comma B. There are several approaches to this encoding which will not address here, but suffice it to say that there are relatively straightforward techniques that can be used as with the key exchange system. An encryption decryption system requires a point G and an elliptic group EQ of A comma B as parameters. Each user A selects a private key NA and generates a public key PA is equal to NA into G. So to encrypt and send a message PM to B, A chooses a random positive integer K and produces the ciphertext CM consisting of the pair of points. CM is equal to KG PM plus KPB. So here note that A has used P's public key PB to decrypt, and the ciphertext B multiplies the first point in the pair by B's private key and subtracts the result from the second point. PM plus KB, PB minus NB into KG is equal to PM plus K into NBG minus NB KG is equal to PM. This has masked the message PM by adding KPB to it, so nobody but A knows the value of K. So even though PB is a public key, nobody can remove the mask K into PB. A also includes a clue which is enough to remove the mask if one knows that the private key NB. So for an attacker to recover the message, the attacker would have to compute K given G and KG. This is assumed to be hard. So by considering here we have a table that shows comparable key sizes in terms of computational effort for this crypt analysis. So security of this elliptic curve cryptography shows that the security of ECC depends on how difficult it is to determine K given KP and P. This is referred to as the elliptic curve logarithm problem, but the fastest known technique for taking the elliptic curve logarithm is known as the Pollard row method. So this compares various algorithms by showing comparable key sizes in terms of computational effort for cryptanalysis. As can be seen, a considerably smaller key size can be used for ECC compared to RSA. Further, for equal key lengths, computational effort required for this ECC and RSA is comparable. So there is a computational advantage to using ECC with a shorter key length than a comparably secure RSA. Thank you.